Yes, welcome everyone to the NCTS webinar on nonlinear evolutionary dynamics. Today, I'm really happy to present Professor Romain Joly from the Institut in Grenoble. So he's joining us from France to tell us about everything generic that has to do with traveling fronts in parabolic systems. So I'm really curious about which generic features Romain will explore today, and I'm really looking forward to your talk.
Okay, so thanks Alejandro for the invitation. So of course, well, online talk it's not always the best, but in this kind of opportunity to present you very far away my work, it's very nice. Thanks. And so I would like to present you some works on traveling front, because I think that it's the main topic of your seminar. And so it's a joint work with Emmanuel Rissler, who is in Lyon. And I just see that the date is absolutely not, it's not serious, but okay. So let's start with the PD. So I would like to consider the parabolic PDE. Okay, so it's a parabolic system, dTw equal Laplacian W plus some nonlinear term. But the important feature is that in my talk, so X is just 1D, it belongs to the real line, okay? But W, it's not scalar, W, it's a vector, okay? So you can see this as a system of several parabolic PDE. And also what is important is that the nonlinear term is the gradient of a potential. So of course, for scalar parabolic equation, it's always the case that in 1D you have the derivative of something, but for a system, it's a very particular assumption. Okay, so okay, I'm interested in this kind of parabolic system. And what I would like to study is traveling front and standing pulses. So in my talk, fronts means a solution of the type U of x minus ct.
Sorry, Romain, can I ask a question?
So,
Romain, can you hear me?
Yeah,
yes. So go back to the previous slide. So you have this partial x squared, so it's a first derivative or parabolic, right? So it should be second derivative.
So it's a second.
Yeah, because usually we just write partial x, but now you write 2. So I was thinking maybe it's fourth derivative in x.
No. It's two derivatives. So it's just the Laplacian, the second
okay.
order derivative. So it's really the heat equation plus some nonlinear term.
I see.
And all the coupling. So what is important is that so W belongs to RD. So you can see this as several PDE. Okay, a system of several PDE, and all the coupling comes from this nonlinear term. So there is no coupling in the linear heat equation.
Oh, good. Thank you.
Okay. Okay. Just please just interrupt me for anything. Just nice. Otherwise, I do not see any people. I do not hear, so it's strange. That's if you just interrupt me. Okay, so I would like to consider traveling front. So of course you know what are traveling front. Just to be sure, I would like to say that in my talk, when I consider fronts, it means that the profile U of the solution converge in plus and minus infinity to two equilibrium points. So they are just a solution 0 of the nonlinearity, so critical point of the potential. And fronts means that both are different. So it's two different limits in minus and plus infinity. And okay, so since this is a system, just you have x belong to the real line, that knows the variable, the profile U belongs to some RD, transverse space RD. Okay, so it's moving at speed c. In my talk, it will be positive c, just by symmetry. You can ask this. And so I talk about traveling front if c is really positive, non-zero. And you can also introduce standing front, like front with 0 speed, but we will see that it's not so important in the dynamics. Okay, so this first class of objects is a traveling front, and the other class of object I would like to consider is pulses. So pulses is the same thing, but the limit in minus and plus infinity are the same. So it's something that is close to some equilibria, do anything non-constant, and then go back to this equilibria here. And again, I can look to this kind of patterns moving, traveling at speed c. But the important case actually is when it's standing. So it's really just a solution which is a non-constant, spatially non-constant, static solution of the PD. So simply this kind of thing. And I will have to split this class in two particular cases. So I have a particular case which is the symmetric pulse, and symmetric pulse means that there is one point, by translation say 0, so that the solution is symmetric with respect to this point. I mean, for example, that even U is an even solution. So these are symmetric pulses, and of course you have non-symmetric pulses. There is no symmetry. Okay, so I would like to study this kind of patterns, and so let me motivate the fact that I'm looking to system with a gradient nonlinearity. So this is very particular structure. So actually, this structure is important for the dynamical point of view, because once you assume that the nonlinearity is a gradient of a potential, you have an energy, and this energy is simply the classical parabolic energy. It's 1/2 the square of the gradient plus the potential energy. Okay, so you have an energy in the static frame, okay, if you just consider the PDE. But what is very important also is that you have this kind of energy in any Galilean frame moving at a constant speed. By this I mean, if you look to a frame moving at speed c, so you have to change the variable. So the new solution is w tilde. Okay, the same but in the moving frame. It solves the same kind of PD, but you have this additional term coming from the moving frame. And if you look to this PD, again, you have an energy, and this energy is the same as the classical energy, but you have this exponential weight here, exponential weight for, and by energy, I mean that, you know, if you at least formally look at this energy, it is non-increasing in time. So you can expect to have some dissipative structure. But the difficulty in this case is that this energy is just a formal energy. And by this, I mean that even if you look to a traveling front, for example, this energy may be infinite. Okay, so there is no reason that this energy is well defined, is finite, and of course it's worse with this exponential weight. But even in the static frame, in the standing frame, this energy may be infinite. And even if you start from a solution where this energy is finite, then it is non-increasing, but it may converge to minus infinity. So you have no information like convergence to equilibria. It's not easy to use this formal structure. It's more a formal structure, but there are techniques to use this. For example, you may truncate this energy, you may approximate this energy by another one, and things like that. So there is a lot of several works who use this energy to obtain a property for this kind of PDE. So for this, I'm aware mostly of two groups of people. One is around Muratov and Novaga. And so mostly they study the case of scalar parabolic PDE, but in a different framework. So in cylindrical domain, things like you have more than just 1D spatial variable. And so in their case, they still have the maximum principle because they work with scalar parabolic PDE, but they are really using this gradient structure, this formal energy, to obtain to have a variational approach, variational results. And they obtain a lot of existence and stability of traveling front using this kind of structure. And another group of people are working with Emmanuel Rissler. And so he's working really on the parabolic system. So there you really, you cannot use the maximum principle. There is no maximum principle. And so this powerful tool which give you a lot of information in the scalar parabolic equation, you cannot use it anymore. So that he just used this gradient structure to obtain a lot of dynamical properties. And so let me just give you an example. So it's a very powerful tool. So more or less, this is like a statement coming from the work of Emmanuel. So just consider again the parabolic system. So W is a vector. You have just the heat equation plus non-linearity completing all the equation, all the spaces. And this non-linearity is a gradient of some potential. So you assume that this potential is coercive, so it goes to plus infinity when the state goes to plus infinity. And also assume that it satisfies some natural hypothesis. And in this case, what you can prove is that if you start from a solution which is close to stable equilibria when especially when x goes to plus and minus infinity, that means that you start from something which is close to some equilibria E minus here and close to some equilibria E plus here. And in the middle, you can do whatever you want. Just it's not a local result. You can really do whatever you want. You start from a solution from a function like this, and you let it evolve by your PDE. And what you obtain is that asymptotically, when t goes to plus infinity, this will converge to a combination of several traveling and standing fronts and pulses. So sometimes they are called terrace, this kind of picture. So it's complicated to describe this mathematically, but just the picture is very easy to understand. Is what you will see that when t goes to plus infinity, your solution will look as there are fronts moving at different speeds. So of course, the front, the more to the right is the fastest front. Okay, and then you have slower fronts moving to the right. Then you may see standing pulses, standing structure there, and then you have also front going to the left. And so you can see after some time, you really see this kind of patterns appearing in the PD. Okay, so to obtain this, you really need this gradient structure. So it's really using this gradient structure. But what is important is that you do not assume anything about it's not so it's not a global a local stability. It's a really global stability. In particular, you do not assume to be close to anything, and in fact, you do not know anything about the traveling wave. So for to obtain this result, you do not know. Even it's not important to know that there are traveling waves. The existence of traveling waves is a consequence of this result. So it's a very nice result, but so there are some hypotheses which are somewhat natural. You expect that they are generic, that they are all for random potential. But so the motivation, the first motivation of my work with Emmanuel was to prove that actually these hypotheses are really generic. But I hope that I would convince you that actually there are also the motivation is not only just to check that the hypothesis of this theorem holds, but also they give you important information about the dynamics of the traveling fronts and standing pulses in the PD. Okay, so let's just present you what kind of result we have, and then I will actually spend most of my talk to explain you in a better way this result. So I consider this PDE system, and for almost all the potential V, for generic random potential V, you have the following thing. First, there is no standing front and no traveling pulses. So the main, the structure, the dynamical patterns are traveling fronts and standing pulses. No other things. Also, every traveling front which invade a minimum point of V is bistable. So I will explain this. But for system, you may have arrayed monostable front, but they just appear for very special potential and not for generic potential. Also, you have that every standing pulse is stable at infinity. You cannot have standing pulse that connect unstable equilibria at plus infinity. And then you also get much more information, such as the set of bistable traveling fronts is discrete, that they are robust for small perturbation of your PDE, and also that the profiles, the asymptotic profile in X is really what you expect. That it means for the dynamics that it approaches the limits with the first eigendirection, the first eigenvalue, the speed, the asymptotic speed is really the first eigenvalue. Okay, so I will try to. Yes.
Yes, just to be clear, and settle it now. What do you exactly mean by bistable when you use bistable?
Okay, so bistable for me, it's when I look to a front like this. For bistable, I mean that both equilibria here are stable, and by stable I mean stable for the PDE. So just look again to the PDE. So this is the PDE, and if you plug something which is very close to the constant equilibria, so E plus, and the small e will always be just vector. So it's if you look to the PDE, if you consider the PDE, it will mean that it's a constant solution. Okay.
Yes.
And if I look to the solution to constant for which the non-linearity vanish, of course it is they are equilibrium of your PDE, just constant, especially constant equilibrium. And by stable, I mean that they are stable for the PDE, which is the same actually that they are stable for in the case of the potential. I mean they are local minimum of the potential. Okay, so bistable means that you have local minimum of the potential here, local minimum of the potential here, and here there is a front, the structure like this equilibria is invading this pattern is invading the other one. Okay.
Thank you. Now it's clear. Thank you very much.
Okay, so and again, it just interrupt me. I was wondering if it's still okay. You can see me, something like that. Okay, so well, these are this kind of results that I can I'm able to show. So this means that in particular, so let's look to this kind of pattern. If I have a stable equilibria, so again a local minimum of the potential. This may be unstable in the sense that you may have invasion with other states for this. And all the pattern of this kind of invasion will look like a discrete set of traveling fronts for which every invasion, the state invasion state is also stable. So also a local minimum of the potential. I will give you a lot of pictures for this. Maybe it will be simpler to understand this. Also, you may see standing pulses. Okay, so if you have also a picture patterns which connect this E plus to E plus also in minus infinity, then it should be at speed 0. Okay, so this is standing pulses. Okay, so this kind of pattern this is generically what you can see for the invasion of a stable equilibria here. So just once in this talk, I would like to precise what I mean by generally set. So it's not so important to understand the picture, but just to give you a precise definition. So actually, what I will prove is that something happens not for all the potential, but for almost all. So almost all will mean for a large set of potential, and there are different sense of this of how you can call what you can call large set, but the result all for any reasonable sense of large set. Okay. So the simplest, the most usual case definition is generic set. So it means that it contains a countable intersection of dense open sets for some topology. So for example, the topology generated by the infinity norm, things like that, whatever what is reasonable in actually it's all for any reasonable setting. So if you are not used about this, just think that generic means that it's almost all. If you take randomly some potential, the result will hold, not for all, but for random one. So for a set of measure one, the difficulty is that it's not clear what measure is the best here, but if you prefer, you can think about this way. Okay, so and just to if you're used to scalar parabolic equation, I just would like to give you an example of what so our result means. So if you look to traveling front, so again, if you're used to traveling front in the scalar parabolic equation, the usual parabolic equation, so there is some categories that are bistable front and monostable front. So when you speak about bistable front, you mean that both equilibria here and here are stable for your PD, so for the potential. So the local minimum is the potential. Okay, so so that's usually called bistable front, and there were also monostable front. In the case of monostable front, usually when you speak about monostable front, you say that this E plus is unstable. So naturally, actually, it will be invited by something, and this E minus is stable. So the monostable case for scalar parabolic equation always refer to this case where E plus is stable and is unstable, sorry, and E minus is stable. And why the other case is not does not appear? Actually, it is impossible. I will explain you that for scalar parabolic equation, you cannot have the other way is that this one is stable and this one is unstable. It's not possible for scalar parabolic equation. So usually when people talk about monostable front, they talk about this situation. But if you look to system of parabolic equation with a potential or not, but any system of parabolic equation, of course, you still have this same kind of front, the bistable and monostable like this, but it's also possible to have the monostable in the other way. I mean that this is a stable equilibria which is invited by an unstable equilibria. So of course you expect that this is somehow unstable patterns that we will not see usually in the dynamics, but this kind of solution may exist. And what say a consequence of the results of work with Emmanuel is that it may exist, but in our PDE, it does not exist for almost the potential, all the potential. So if you take a generic potential, this kind of solution of traveling front, monostable but reversely monostable traveling front, does not exist. So it's not that it's just unstable, it really means that it does not exist. Okay, so if you use to the scalar parabolic equation and bistable, monostable front and things like that, it's one difference with this system and one of the consequences of my work. Okay, so is there any question or still okay?
Can I guess that the difference between scalar and the system of PDE? So one is impossible, the other is possible because now for systems we don't have maximum principle. Or what is the main reason for this?
So so what is the difference here? I will just present you just after. I will explain you correctly why it is impossible to have this kind of front in the scalar and why it is possible in the system.
Okay.
So I just actually it will be most of my thought. I think I will not tell you anything about the proof, but I would like to now to explain you how you can see all these kind of results to get this intuition, to get this insight.
Yes, nice.
Okay, so let's now explain this. And so here is maybe you will be disappointed because here is a place where I will tell you that it is not a PD talk. It's actually it's more an OD talk. And I will. So what I would like to do now is to explain that the study of traveling front and standing pulse actually is more think about the dynamics of OD. So why? Of course, is that if you look to traveling patterns, so solution like u of x minus ct, then okay, you just plug this kind of type of solution in your PDE, and what you will get is that this profile u must solve some OD, which is just a second derivative of u equal minus c u first derivative of u plus this non-linearity gradient of v of u. Okay, so it's just an OD in RD, okay, because your profile is just some profile in RD. And okay, so of course also you must be aware that since it is OD in RD but a second order ODE, it means that actually the real phase space is R2D. I mean that the real variable of your ODE should be capital U, which is U and U dot. Okay, and so you have really a ODE in R2D. Okay. So actually, to study traveling patterns, I have to understand what are the possible solutions of this kind of ODE. So let's look first to the case, to the Hamiltonian case. That is the case where C is equal to 0. So when C is equal to 0, it's very particular because you have an Hamiltonian system. I mean that the standing, you're looking to the standing patterns that are the non-constant, spatially non-constant solution of your PDE, and they are simply solution, of course, of Laplacian U equal gradient V of U. And you can see them as trajectories of an Hamiltonian system. And because you have an Hamiltonian energy, that is an energy which is conserved by the flow of this ODE. And this energy is simply the classical energy where you have 1/2 of the speed square plus the potential energy. Okay, so if you look to this Hamiltonian energy, so it's conserved by the flow, the solution U, when x move, this is conserved. And what I would like to say, okay, it's really the classical energy for the mechanics, for the Newtonian mechanics. By this, I mean that this is the kinetic energy, and then you have the potential energy. And so you're ready to get the insight of mechanics. Since there is a minus V, it's better to consider V tilde, which is just the opposite of V, so that you really get this kinetic energy plus potential energy, where the potential for the mechanic point of view is this V tilde. Okay, so now actually when you consider standing patterns, so patterns like this, what you have to understand is what happened for this ODE, for this Hamiltonian systems. And this Hamiltonian system is just mechanically the same thing that a ball which is rolling on the surface without friction. I mean that if you just consider this is for the mechanics, it just means that you have a ball, okay? You have your surface, which is the potential, so V tilde, which is minus the potential for the PD. So you have this gymnastic to do. Okay, but it's the reverse of the opposite of the potential of the PD. But you have a surface like this, and you just let the ball roll on the surface, and you just look what happened. Okay, and if you look to the trajectory, for example, to a non-symmetric pulse, it means something which starts from one equilibria at minus infinity and go back to the same equilibria at plus infinity. So this means that for you are playing the following game, you have, for example, here you have a stable equilibria of your PD. So it's a local minimum of V, so it's actually a local maximum of your potential. You start with a ball here and you slightly push the ball in some direction so that they are rolling on your surface. And then like a skate park, it's just go back, then just go back to the, when t goes to xi goes to plus infinity, to the same equilibrium point, okay? So you just have to find trajectories that look like that, and it will correspond to the trajectories of non-symmetric pulses. Okay, and for symmetric pulses, so it's very particular. Actually, you can show that symmetric pulses see the same thing at this behavior. You just push the ball, it starts to go down here, and then it's going up somewhere, and at some point the speed vanish. So, and once the speed vanish, the speed of your ball vanish by reversibility of the for time, okay, time reversibility of the OD, then the ball will come back again with exactly the same trajectory. So this will provide you symmetric pulses, and symmetric pulses are exactly this one. The ball is rolling, then just stop, and then to go back to the equilibrium point. Okay, so to understand what are the possible pulses, this kind of pattern in the PDE, you just like to understand what happened for this mechanical system. Okay. So once you have this point of view, there is a very simple result, which is that since the energy is conserved by the flow, it means that if you try to have standing front, so something which with the zero speed but which connect different equilibria, it will mean that we will start from some equilibrium point, the ball will roll down here, then go up, and then just stop to the other equilibrium point. And in this case, it's only possible due to conservation of the energy if both equilibria have the same energy, the potential, okay, the same value for the potential. And so it may happen, okay, you can construct particular potential so that they are really this kind of trajectories, not too difficult by symmetry, but it's very particular. And actually, it's very easy to see that if you take a random generic potential, you will never have two equilibrium points with the same energy. This means that it's never possible to have this kind of standing front, okay, this kind of connection between two different equilibria in the Hamiltonian case. Okay, and exactly that what is written here, that for generic potential, there is at most one equilibrium point for each level set of the energy. So what is called heteroclinic orbits for the ODE, so orbit connecting two different equilibrium points, then these heteroclinic orbits are not possible. Okay, and for the PD, it means that there are no standing fronts. So the fronts are always moving at some speed. It's not possible to have zero speed front. Again, it is possible if you choose very particular potential, sorry, but it's not possible for most of the potential.
So am I right to understand that then you need friction, essentially, some sort of friction, right?
So here, when you consider the case with speed zero, so yes, really the standing patterns, there is no friction.
Yes, precisely.
Yes, and so
if
when
C is non-zero,
we will consider traveling front, you will have this friction term. Okay,
I see. Very interesting.
So it's exactly this thing. Okay. So here there is no friction, so it's very particular, and you have no standing front generically. And okay, now you consider, so it means that the important things are what is called homoclinic orbits, that are solutions that start from equilibria and go back to the same equilibrium. It's the only thing you can see these pulses. Okay, and to obtain important feature about these pulses, you have to understand what is called the local stable and unstable manifold. So I'm not sure how much you know about this, but just to get you a slight insight is that if you consider a particular equilibrium point, okay, so you can introduce the Morse index of the equilibrium point for in this talk, there is several definitions, but in this talk, Morse index is just the number of negative eigenvalues of the Hessian of the potential. So I mean that if I have a stable equilibrium for the PD, then this Morse index is equal to 0. It is a local minimum of V, so a local maximum of V tilde, which is the opposite of V. So this is a point where you have the Morse index 0. This is a point where the Morse index is equal to 1 because I have one direction which is stable, one unstable direction. And these are local maximum of the potential, local minimum of V tilde. And in this case, the Morse index is equal to 2. Okay, and once you get this Morse index, it's really easy to see that for the ODE, the Hamiltonian system. So if you look to the equilibrium point in the R2D, in the ODE, then you have this kind of pattern. There is a stable manifold, so all the solutions that are attracted by your equilibrium point is a manifold, and this manifold is of dimension d minus the Morse index. There is also the trajectory which are repelled by your equilibrium point. Okay, it's an unstable manifold, and this unstable manifold is of the same dimension, d minus the Morse index. And also you have a center manifold, and this center manifold is the missing dimension to a Morse index of E. Okay, so just to give you an insight, it just means that if you look to this kind of equilibrium point, you have a dimension 2 set of solutions which are repelled by your equilibrium. It's just a solution that you push the ball and they go back and they go downhill. Okay, so a dimension 2 of solution which are repelled by the equilibrium point, and you have also a dimension 2 of solution which are attracted by your equilibrium. So it's exactly you reverse the time, so it's a solution so that the speed is exactly the correct speed, so that they will converge to this point here. Okay, so 2 dimension for the unstable and stable manifold. In this case, where I have Morse index 1, I have this solution, one dimension space of solution which are repelled by the equilibrium. So you just push the ball and they follow this valley here. Okay, but I also have a center manifold. So what looks like the center manifold? The center manifold actually is the kind of solution which are just like periodic solution, just rolling like this on this curve. Okay, so they always stay close to the equilibrium point, not repel, neither attract by your equilibrium point, and that's what is called the center manifold. Okay, and if you have a local really unstable equilibrium for your PD, so local minimum of the potential, then you have no stable and unstable manifold, and actually you just have a center manifold, which is like a tori of solution where just rolling close to this equilibrium point. Okay, so this is a picture close to some equilibrium point, and what you can show really rigorously, just not considering this picture, but is that in fact actually this center manifold has no importance in your dynamics, because this center manifold always just contains like a locally tori, invariance tori and things like that. And in particular, it does not contain anything in which is attracted with your equilibrium point. Okay, so it means that the homoclinic orbit, what is called the homoclinic orbit, so the pulses are just in the intersection of the stable and unstable manifold. It's just the thing you have to consider. So why it is important to look at this is because now you can argue something by dimension. So the picture is the following. Again, you have an equilibrium point of your ODE, and you're looking to pulses. So things like converge in minus and plus infinity to the same equilibrium point, which for the ODE point of view, it's called homoclinic orbit. So an orbit it's U, so that you start from your equilibrium point and then you go back to your equilibrium point. Okay, so this kind of solution belongs both to the unstable manifold of the equilibrium point, because they are repelled at minus infinity by your equilibrium point, but they also belong to the stable manifold of your equilibrium because they go back, they are attracting at plus infinity to your equilibrium point. Okay, so if you want to have something which is really robust, then the right condition, geometric condition, is that the unstable manifold and the stable manifold intersect transversally, just like in the picture. So transversally just means that if you look to the tangent spaces, they generate the whole space. Okay, so the sum of the tangent spaces really generates the whole space. So this is the transversal intersection. Non-transversal means that you have more tangency and is missing direction in the tangent spaces. Okay, so you would like to consider this transversal intersection, to have this transversal intersection. Okay, and what you have to notice that the dimension, if you look to the dimension, is that if I have a Morse index here which is not 0, then the both W, the unstable and the stable manifold have dimension D minus M of E, and then you have not enough dimension to generate the whole space. So it is not possible to have transversal intersection if the homoclinic orbit, if you consider not a stable equilibrium. Okay, so it's one thing. And the other thing, it's more technical, but it's like even if you consider a trajectory with a stable equilibrium here, so this means that the unstable and stable manifold have dimension exactly D. Okay, so you would like to generate a space which is of dimension 2D, so it looks good, but actually there is an intersection, because you know that there is this trajectory inside the intersection. So you cannot do better than dimension 2D minus 1, because there is here dimension D, here dimension D, but you have an intersection of dimension 1. So you cannot do better than 2D minus 1, and your space, the whole state space, is of dimension 2D, so it looks like it's a fail, but not really, because you have to remember that you have an Hamiltonian dynamics, and it means that all the dynamics is contained in the level set of your Hamiltonian energy. So due to this, you have a conservation of energy. It means that the whole interesting dynamics belongs to a manifold of dimension 2D minus 1. So actually, it's a correct dimension to hope to have transversality. Okay, so this is the problem of transversality if you look to homoclinic orbit to obtain this kind of thing. So what we will do actually is to prove this kind of transversality, and I will explain you why there is some consequence for the patterns of the PD. Okay, so this is the point of view of the dynamical point of view for the OD. So what we can prove is that for a generate potential, actually the non-symmetric homoclinic orbits are transverse, in the sense that, again, you have this picture that the tangent spaces of the unstable and stable manifold intersect transversally inside the level set. Okay, so this is a result, but just for non-symmetric homoclinic orbits. For homoclinic orbit, actually, we don't know for the moment.
Romain, may I ask a question?
Yes.
Because whenever
Yes.
I see transverse homoclinics, I think of the small horseshoe picture, right?
Yeah.
So I think of chaos.
Okay.
But
yes. So this means.
Yes.
So this means that it is possible. You may have. So I'm not sure due to this conservation of energy, but just to forget this, of course, you're right. If you have homoclinic orbit, you have chaos. Okay, so this means that close to this standing pulse you create here, you have chaos. So what is mean for the PD? So I'm not sure if I have some like, okay, like, so you have a pulse like this, okay, and once you know that this corresponds to a transverse homoclinic orbit, you're right to say that you expect that there are chaos close to this. But what is mean chaos? It means a solution of your PD which is close to this one, and which has a behavior which is, for example, non-periodic and very chaotic behavior. So you create something which is like a standing pattern of your PD, but a standing pattern which is not a pulses because it's not converging to equilibrium point here. But you're right that it shows that you have a particular equilibrium point for the PD. So really a static solution of your PD. May have very complicated. Also, it shows that you have periodic orbits. Smeg also says that you have a lot of infinity number of periodic orbits. So spatially periodic solution of your PD, standing solution of your PD, close to this one. But if you consider just like traveling front or traveling or standing pulses, they say that just once, because again, this condition that you may converge to equilibrium point and plus and minus infinity. Okay. So you're right that. So what I would like to actually is more the only thing I would like to explain here is that the behind what I say about the patterns of the PD, I have actually some dynamical feature for the ODE, and from this dynamical feature, the transversality of homoclinic orbit, I may deduce something about the pattern of the PD. So here I deduce that the fact that the standing pulses cannot connect unstable equilibrium of the PD. So if you look to this kind of pulses, there is always pulses for the stable equilibrium point. They are possible, but not for the unstable equilibrium point. This is one of the consequences, but you're right that the fact that there are also very chaotic standing solution is also a consequence of this result. So this is the real result, behind the thing. Okay, and from this result, you can deduce several things about the PD. So here I just present you the case of non-existence of pulses if you have unstable equilibria, but you're right that they also give you some particular solution, chaotic solution, and so on.
Very surprising.
Okay, so and so also, for example, another consequence of the transversality is that the profile of these pulses are isolated from each other. So you cannot have a continuum, a line of pulses, so like a profile which are very close, a continuous deformation of the same profile. So it's always possible to construct this kind of thing, but if you choose very particular potential V, and if you just take a random potential V, you will not see this kind of things. Again, it's just a consequence of the ODE things, the transversality of the ODE. Okay, so as you can see, just concern non-symmetric homoclinic orbit. Actually, we don't know what happened for symmetric, the transversality for symmetric orbits, but we still have a result for symmetric orbit. So just I would like to explain this. So if you look to symmetric homoclinic orbit, so again, you play with this ball and you just push this ball from the equilibrium point, and we'll just go at some point where the speed vanish and just go back like this. Okay, and you can prove that this is really what happened. This is the only possibility to get symmetric homoclinic orbit, and this means that if you look to know geometrically what happened for the ODE, it means that you have a symmetric homoclinic orbit as soon as you have a solution, an homoclinic solution, which meets the place where the speed vanish. Okay, so this is geometrically, it just means that you meet the manifold RT times 0. Okay, so it's just the place where the speed vanish in the phase space. Okay, and so geometrically, what you can hope is that again you have transversality, but not transversality of the stable and unstable manifold, but transversality of this stable and this manifold, and this particular manifold, like the turning point manifold, the place where the speed vanished. And this has a name, actually, it's called elementary. So a symmetric homoclinic orbit is called elementary if the unstable manifold meets this manifold where the speed vanished transversally. So again, it's a robust geometric assumption, this thing. Okay, and this definition of elementary, this assumption that elementary. Actually, it's surprising, but it has its own interest. And just for the reference, I have already seen this kind of definition. Exactly, this definition comes from the work of van der Bovede and Fiedler. Not recent, but old words. And so it's in this work they prove that once you have this, the fact that symmetric homoclinic orbit is elementary, you can get some interesting dynamical feature. Again, we look into this. So it's weaker than transversality, but for symmetric homoclinic orbit, it still have some consequence and interesting property. And what we were able to prove is that for generic potential, for almost all the potential, then the symmetric homoclinic orbit are actually elementary. Again, once you have this, you can use this to obtain several properties like the work of van der Bovede and Fiedler, but you can use this to translate this in the patterns of the PDE. And so what you can say, again, if you look to standing pulses, it's that, again, the symmetric standing pulses only connect stable equilibria. You cannot have this picture, this pattern, where you have standing pulses that connect unstable equilibria. And again, you have robustness and things like that. They are isolated from each other due to transversality and so on. The only thing, just to give you one difference between the fact that the difference, since we just have elementary and not transversality, and since it is weaker, you know that the profiles of symmetric pulses are isolated from each other, but you may have a sequence of non-symmetric pulses, sequence of profiles of non-symmetric pulses that are close to the symmetric pulses. Okay, so this is the only difference where you can see the fact that we get just elementary and not transversality. Okay, so again, you have a proof, you obtain something about the dynamics of the ODE, and you deduce some properties of the PDE, but maybe more properties than these simple properties. Oh no, I have a very few time to consider the case of traveling front. Okay, so just I will play the same game, but for traveling front, and actually it's the only place where we can see that there is a PDE. I will show you. So now consider the case where the speed is positive. Okay, so non-zero. So you look to traveling patterns, so solution like which look like this, and the profile then solve this ODE. So it's again just an ODE, the same kind of picture. There is an energy, but no, as you said, there is a friction term. So you can see that this term is just a dissipation of the energy. The energy is no more conserved; it's just dissipated by the parameter C. Okay, so now the game is the following. You consider two equilibrium points, okay? And if you want to have a profile of a traveling front connecting these two equilibrium points, you play the game with a rolling ball, okay? You let the ball go down here, there. But what you can do also is that not only you choose the direction where when you push the ball, but you also choose the friction, so how much you break. Okay, and so that is possible now to have, if you break enough, to have a solution that goes there and just break, just to have a solution to go to this equilibria, which is a lower energy, but since you have break, it's possible. Okay, so you have two parameters, now like the direction and the how much you break, so it's the choice of the speed, actually. Okay, so this is the difference. And so I will not detail too much there, but actually, if you look now again to play the question of dimension, you will see that it is not possible to get transversality of stable manifold of some stable equilibria and the stable manifold of anything. So you cannot opt to have transversality in your ODE. And the reason why you cannot have transversality for your ODE is because when you consider the ODE, the speed C is fixed. So you have an ODE like this, and you fix the speed. Okay, and in this case, you know that traveling patterns are not robust because you expect that when you slightly move the potential, for example, your traveling front will stay, but maybe the speed will slightly move. So for the ODE, it just disappears because it's ODE, just the speed is fixed in your ODE. Okay, so there you have to play with a game which has both. You have to consider the ODE and the fact that the speed somehow is the freedom, it's the degree of freedom in your pattern. And this is the only place where you can, in this talk, where you can see that we are working in a PDE. And so just I would like to show you. So exactly, I mean that you have the freedom, the degree of freedom, which is the speed of friction, C here. And so we introduced Emmanuel a definition, which is, I think, one of the interests of this work. And this definition is the only one where you can see that we are working in PDE. So the transversality, if you look to the standard transversality for ODE, again, for traveling front, it's not interesting. It will not give you anything. So we introduce a notion of transversality for traveling front. And it is the following. So you consider the patterns that are solution of your this ODE with the speed C, and you consider what happens when your speed C is moving. So you're not only considering the unstable manifold of your equilibrium point at a fixed C, but you're looking at what happens when C is moving also. So now you have a state which is given by the speed and the ODE. So you have both things. And the same for the stable. And now the transversality of the front means that in this state space where you have both the solution of your ODE and the speed as a parameter, the two manifolds here are transverse. So this is a definition of transversality that is the correct definition for traveling front. And so it's not a definition which is pertinent in the relevant in the case of ODE. So I never seen this about ODE, dynamical system, and so on. But if you look to traveling front, this is the correct definition of transversality. Okay, so this is one of the interests of this work to show that this is the correct definition of transversality. And again, then you play the same thing, is that you show that this transversality holds for almost all the potential, and it will give you some information about the PD. Okay, so just to give you again, is that once you get the transversality, generic transversality of this for the profile of the front, it will show you that the only traveling front that connect two equilibria where E plus is stable, they are the bistable front. Okay, and just to maybe to finish and to let place to question and discussion, I just want to present you why in 1D in the scalar parabolic equation this kind of front they are always bistable and non-stable in one type and not non-stable in the other type. So I just want to finish on this. So in the classical case of scalar parabolic equation, the picture is the same. Of course, I'm 1D, so no, the potential is just a real function like this. Okay, but it's always the same thing. If I'm looking to traveling front in the usual scalar parabolic equation, what I'm playing is a game at let the ball roll, start from a stable equilibria, so local maximum of minus V, okay, and I let the ball roll, and I want to break enough so that I will just finish at some point another equilibrium point. So you see that if I'm considering bistable front, I have to break exactly the correct way to stop here. If I break too much, then I will not get there. If I do not break enough, then the speed C is not strong enough. Then you will just roll and go other way. Okay, so this is exactly the insight telling you that bistable front in scalar parabolic equation just happen for one speed C, or at least for very special speed C. If you look to monostable front in the sense that the E minus is stable and E plus is unstable, then what you get is that you have an infinity number of traveling front, monostable traveling front, and there are this traveling front where you break just slightly so that you have an oscillation like this, and you finish at the E plus here. So this is one case, but they are, so for the usual PDEs, they are not very interesting because often this is 0, and so it's a negative solution. So often it's not what you would like to do. But also you have that if you break enough, then you will start from there and stop here without any oscillation. So if you really have a strong break, so it means that if your speed C, so the friction C is large enough, then you will see a solution, a monostable front, going from there to there. But also, if you break more, you will always get that you have a solution, your ball will stop there. So this is exactly the insight that the monostable front in the scalar parabolic equation, they are possible once you get C larger for some speed, and after this speed, there is always a family of this monostable front for all the speed that are larger. Okay, but in the scalar parabolic equation, what cannot happen is a monostable front when you start from unstable. Okay, so you have an unstable equilibrium which inviting something, and it is not possible because if you start with your ball there, of course your ball will not move. So you cannot see anything like monostable front where the equilibrium in minus infinity, the invader is unstable. Okay, but in a non-scalar case, in the vectorial case, it is possible because of course what you add is a transverse direction like this. So in this transverse direction, it may be good downhill. In this case, you can start from there, and the ball may roll and attain another equilibrium like this. Okay, so this is why this kind of particular monostable fronts, like reverse monostable front, are not possible in the scalar case, but they are possible in the vectorial case. In systems, they are possible. And again, one of the consequence of our work with Emmanuel is that even if they are possible, they are very rare. They do not happen for generic potential. Okay, so let me stop there, and thank you very much for your attention.
Yes. Thank you very much for the talk, Romain. It was something. I mean, I'm definitely not an expert in PDE, but I can tell that many of the concepts you introduced today were new, and certainly these new definitions of transversality, sort of in extended phase space, are something we're looking at, right? So yes, sir.
Yeah, if you have question, I'm
yes.
I'm free.
Yes. So if anyone in the audience has questions, feel free to ask, and feel free to just open up the mic. Otherwise, I have plenty of questions. Then I will just go ahead, I guess. It's important that all of these genericity results are within the class of gradient of PDEs whose nonlinearity come from a gradient, right?
Okay, so when you have so first I will consider this gradient case due to the motivation that somehow this kind of thing was the assumption of in the result of Emmanuel. So just go back there. Okay, so in this result saying that the global stability of terraces somehow you have this hypothesis, and for this result it's very important because they are using the gradient structure that you have a gradient here. Okay, so first thing that we start to study this case due to this. Now you can ask what happen if you just consider okay, a system of parabolic equation where we have a complete term, a nonlinearity, which is not the gradient of something, which is very relevant if you look to biology, chemical thing, and things like that. And okay, it's always there is a balance in this kind of result because which is the following. if you want to prove a generic thing, so that something is true for a generic potential V, for example, okay, if you consider nonlinearity, which is the gradient of V, it means that you have less freedom to move this nonlinearity. Because, for example, if you want to do something like a perturbation which change slightly your trajectory in some way, so you want to slightly move your your nonlinearity to obtain something, then of course, if you want to be the gradient of the thing, you have a constraint. You cannot do whatever you want. You cannot construct whatever the nonlinearity you want. Okay, so it's there are constraints coming from the fact that you are the gradient of something. But also, since you are the gradient of something, you get this you get particular properties, and of course, these properties are like the conservation of energy for the Hamiltonian system. So, and this kind of things are also can help you. So there is a balance between more freedom mean it's easy to construct things, but less freedom gives you more property that can help you to construct the things. Okay, so it's you have a balance between this, and so here we are able to obtain these properties, the transversality and so on, in this kind of gradient things. Okay, so it's natural to ask what happens if you have non-gradient non-linearity. So the answer is I don't know. Okay, so, but it's a very natural thing. Just even for the ODE, in the ODE point of view, for example, if I just consider this, so the Hamiltonian ODE, it's a natural question for in the dynamical system, finite dimension dynamical systems, looking at what happened to the homoclinic orbit of Hamiltonian system. Okay, and so it was unknown to my knowledge that homoclinic, at least some of the homoclinic orbit are transverse. And what you may ask is what happens if you have no ODE with it is not the gradient of something, but then of course you left the Hamiltonian system. Just really you have an ODE in R2D and you want to have generic transversality, and it's more difficult in some sense.
It's really not a criticism. It's only just a small consideration. But
yes, but it's very important. I'm not taking like it was not a criticism.
No,
it's really important
like
to know that
it reduces a very complicated PDE problem to geometric properties in finite dimensions, and it really gives an intuition of why these things are happening back in the PDE system. And I think that for this, you need to have the structure, otherwise you're completely lost, right?
So somehow for the ODE point of view, like Hamiltonian systems, since you can see them like the mechanical system, the ball rolling and so on, somehow this is completely relevant to consider this gradient structure, because it's really, for the physics, it's really a usual structure. For system of parabolic PDE, so I agree that it's not clear if it is really very relevant to consider this. So mathematically speaking, it is very important. It's a very important structure. But if you look to application, it's not clear in what application you have this gradient structure. If you look to biology, for example, there is no chance that the coupling, the nonlinearity has some gradient structure. It's not very usual, but for the structure of the PDE, so mathematically speaking, it's very important. So for the ODE, it's natural. For the PDE, it's not. The system of PDE is not clear if it is natural or not. But for the mathematician, it's very important, because again, what you have is that for scalar, so the scalar case, you have two features, which is that you have a maximum principle and you have a gradient structure. If you look to parabolic system, then you have it's not clear if you have again a maximum principle and a gradient structure. In some case, if you choose very carefully what is the coupling, you may have again this maximum principle, or you may have, you can choose to have this gradient structure. Okay, so it's a way to keep one of the two main properties of the scalar parabolic equation when you consider systems. But it's not clear if you consider some application if it will get this structure or not.
And here you dealt with traveling fronts, but in principle, I could expect these because now we are dealing with higher dimensional ODEs, right? So one would expect these Hamiltonian level sets to contain very complicated dynamics as well, maybe.
Yeah. So somehow here I just consider the case where the patterns have limits when t goes to plus and minus infinity. Actually, it's really saying that is that in this kind of result, and if in our result the patterns we are looking for is patterns where your solution is constant at plus and minus infinity, close to plus and minus infinity. Okay, so it's really this kind of pattern. If you want to have more complicated pattern, like for example periodic solution or spatially periodic solution, something like that, then of course it's more complicated. It's not included in this result. As you said, once we get this, the fact that there is transversality for pulses that are transversality for the homoclinic orbit, it means that close to this we have a lot of complicated dynamics and complicated patterns. So if you look to patterns which are not connection between equilibrium points, then you have to study not homoclinic orbit and heteroclinic orbits, but other kind of patterns is your ODE. So you can do the same thing, just at least this is the simplest case. Somehow the simpler case is just equilibrium point. Then you look to something which is close to equilibrium point at plus and minus infinity, and then the next level will be to understand what happened for more complicated patterns. It's really depends on what you're interested in.
Yes, thank you.
Could I ask a question?
Yeah.
Yes. The first one, I have two questions. The first one is if I want to add some symmetry to the potential V. For example, I am thinking about a Duffy oscillator is even symmetry, for example. Then if I consider the perturbation in this class, generalized in this symmetry class, do we have a similar result? Or if we have more symmetry, then we have a stronger result, not just generic or something is changed. Have you thought of that?
Well, so it's exactly what I said, that the more you put constraints, symmetry, the more you have properties to use, but the less freedom you have to construct your particular case. Okay, and so at first it's not clear. I cannot say, so I'm not considering this, but I cannot say what is the balance. It is possible that if you add some symmetry, then you can prove even the transversality of the homoclinic orbit symmetric or not, for example. It's possible that you gain this, but it's also possible that everything will disappear and things like that. So it's if you look to the OD, the people, the dynamical systems, people come from dynamical system and so on, so work of like Snell and Kupka and so on, so very old work now, and classical works. And in this case, they always consider just a non-linearity without any assumption. Okay, but if you start from looking to application, to PD and things like that, then it's very natural to have symmetry, to stay in some classes, and then you have to adapt every result in this kind of classes. It's not clear if you in this class what you will gain between what will win between these two things. The constraint will give you too much constraint, or it will help you. It's not clear. For example, in PDE, so it's not. I will not explain this, but it should be too. it will take too much time, but it's known there are results in PDE saying that you will get generic transversality for this class of PDE, and again for this class of PDE, and then you take a class of PDE which is a smaller class with too much symmetry, and in this class of PDE, then the transversality is not generic. So we know example where when you take too much symmetry, then you fail to have this kind of thing. So it's not clear, I cannot tell you, but if you're interested in particular case, because you have motivation to do this, then we have to look at this.
Thank you. Thank you. Yes.
Well, of course, it's quite natural to ask something like, yes, what if you choose SO2 equivariant potential, right? Like,
Yeah.
try to go for an integrable system. Like you have a Hamiltonian, or try to make it integrable or something, right?
And some of the Hamiltonian systems give you some too much symmetries, for example, due to conception, but you have to adapt things. That, for example, the fact that you stay in the energy level in some level set and so on. So it's not clear. Also, you have to adapt the definition on what you are really looking for.
Yes. Yes. Interesting.
Could we construct a stable or standing path for gradient system?
Stable what? Sorry?
Standing path is stable or unstable for gradient system.
Okay, so for this gradient system, somehow the result of Emmanuel Rissler says that the standing pulses, if the standing pulses connects a stable equilibrium point, okay, so you have stable here and stable here, and you make a pulses, it is somehow locally stable. I expect that this is true. Because actually the proof, it's really a proof using the gradient structure. So it's really what you can imagine. So if you avoid, if you forget all the technicalities, it just says that you have an energy, you are dissipating, you dissipate the energy, and so your standing pulse is somehow a minimum of the local minimum of the energy. So if you start locally close to this standing pulses, then you will stay close to these standing pulses. So I expect that it is true. So, well, you have to look, but I expect that it's a consequence of this kind of thing.
Thank you.
And you also mentioned that some people are studying like a traveling wave in a cylinder. There's a bounded section, right? And
Yeah.
here you can see the whole like real line X. How about, do you think you can generalize your result easy to like cylindric domains?
Okay, so it's what I can say that, okay, so for cylindrical domains, in this case, even for the scalar parabolic PD, you can say, you can use the same point of view, is that either, so no, your transversal space is not RD, it's again a PD, so, but you can see your front has a homoclinic orbit and heteroclinic orbit in the PD, okay? So you can play the same game. And so what I can say is that the work of Emmanuel Rissler, so this result, hold also for the cylindrical domain. Okay, so if you add now from X some variable Y, and which also belong to the transverse space, then the same techniques can maybe apply. So there are very robust techniques once you have the gradient structure. It's, all the techniques of Emmanuel are very robust, but you need this gradient structure. And so it's for cylindrical domain, it's it works. There are papers from Emmanuel Rissler on this. But for all the transversalities, the things like that I explained to you, well, it's not clear, because the difficulty is that even for the scalar case, then you have to consider homoclinic orbit, not in OD, but in PD.
Yes.
Okay? And so, of course, it's more complicated. So I have played this game during my PhD thesis. So, of course, it's also natural. But it's yes, it's an interesting question. Mostly, I have no time for the moment to look at it, but it's a natural question. So, and again, you expect that you have some transversality. So generically, with respect to the potential, you expect that this traveling front connecting two equilibrium of the transverse PD will be stable in some sense.
Okay. Thank you. Thank you.